Hey, I think we got the screen fixed. It was always due to my um, ignorance, I suppose. Um, I had talked about the what I call the monster theorem here in this textbook. Well, I think all textbooks except me call it the theorem of equivalence. Here, one statement, if it's true, then all the other statements are true, and so uh, this is what I've basically been using. Um, and for the spanning, you're trying to show this, but since B is arbitrary, all you have to do is if you can take the matrix A and if you can find its inverse. Notice here that for the equivalent conditions, the matrix has to be square. That is, it has to have the same number of columns as it has the number of rows. The rows, number of columns, number of rows must be the same. You notice some of the matrices that we had, that was not the case, and so because of that, then you can't use quite directly the equivalence theorem. And we ran into a situation with a problem with the spanning where once you have that information, how do you interpret it? But all of these are equivalent, and again, feel free to use them. Uh, if you're trying to get one that's hard to get, then maybe get this one. That's easy. This number three is good for linearly independence. That's exactly what you're already trying to do, and we'll talk about that in just a moment. Number four, easy on your calculator. A is reduced to the identity matrix. Five is the determinant not equal to zero. And we hadn't talked about six, seven, and eight yet. Okay. So let's talk about linearly independence. First, we give the definition for linearly dependence. A set of vectors v1 to vr in a vector space V are said to be linearly dependent if there exist scalars k sub 1, k sub 2 to k sub r, such that the linear combination of the vectors with the scalars is equal to 0, but that implies that not all of the scalars are 0. And so uh, that's important. That conclusion is the key for linearly dependence. Let's take an example, and I put examples, but I'm only showing you one. So here S consists of the set S consists of three vectors. How do we show that the vectors are linearly independent? We take the linear combination of the vectors with scalars equal to 0, and then we solve for the scalars. So if we can write one vector as a linear combination of the other vectors, then the vectors are said to be linearly dependent. This also means that we can write here another way to show linearly dependence, that if we can write k1 times v sub 1 plus k sub 2 times v sub 2 plus k sub 3 times v sub 3 equal to 0 for scalars k1, k2, and k3, such that k1, k2, and k3 are not 0, or are not all 0, then the vectors v1, v2, and v3 are linearly dependent. For this problem, and notice how the argument basically kind of falls along the same line as spanning, because within the definition for spanning is linear combination, and within the definition for linearly independence and linearly dependence is the definition for a linear combination. Excuse me. So to show linearly independence, we definitely need these scalars, because those scalars from the system are the same scalars up here that we need to show whether they're all zero or they're not. If they're all zero, then we get linearly independence. But here we're only concerned about linearly dependence. And that's always a question of students. How do you actually show that? What does that actually mean? So we give this example. We have these three vectors, and we write the linear combination of these vectors set to equal to 0. I put this into my graphing calculator. And when I reduce, notice here I get a row of zeros. That's always like an uh-oh. If you get a row of zeros, it's not going to span. It's not going to be linearly independent. What we do get is an infinite set of solutions. You go back to chapter 1. You remember we had something like this. What do? You find the infinite set. So here you would let, since it's k1, k2, k3, let k sub 3 equal to t. And then you get x sub 1 plus t equal to 0. So you get x sub 1, or that is k sub 1 equal to negative 1. And then, negative t, that is. I'm up here. and so k sub 3 is set to be the floating parameter. Is equal to t. And then for that second row, that tells us that k sub 2 minus 3, k sub 3 is equal to 0. That is that k sub 2 minus 3 times t is equal to 0. K sub 2 is equal to 3t. So since this is an infinite set, you can always just pick, one value just to get one set. So what I do here is just pick k sub 3 to equal to t, and if I get that, then that means that k sub 1 is negative 1 and k sub 2 is 3 right here. Now, thus we can write the vectors v1, v2, v3 as linear combination where I get 0. You can pick any combination you want of the k1, k2, k3 as long as they're multiples of the t in that combination form. And you'll get that combination here for this one, negative 1 times v sub 1 plus 3 times v sub 2 plus 1 times v sub 3 is equal to 0, where the scalars, what are the scalars? The negative 1, the 3, and the 1, where the scalars are not all 0. Thus we conclude that the vectors v1, v2, v3 are linearly independent. That's what this definition means. Again, it says that a set of vectors v1 to v sub r in some vector space is said to be linearly dependent if there exist scalars k1 to k sub r such that the linear combination of the scalars and the vectors set to equal to 0 implies, that's the key to the definition, is the implication. Where are we going? Here, this implies that not all the scalars are 0. Well, can we show that? Well, we just gave an example where we just did, right? So, cool. So now, the definition for linearly independence. The definition is very similar. The conclusions are different. A set of vectors v1 to v sub r in a vector space V are said to be linearly independent if there exist scalars k1, k2, and so on to k sub r, should be a comma there, such that the linear combination of the vectors with these scalars equal to 0 implies that all of the scalars are equal to 0. Here we get linearly independence. Getting those scalars to be 0 means that each vector basically exists on their own. I cannot write a vector as linear combination of the others. So that's the thing. Back in that previous example, you can write these one vector as linear combination of the other vectors. Let me show you. try to erase some of this stuff here so I can actually see. All right. So if you look at this equation here, then what that tells me is that v sub 1 can be written as 3 times v sub 2 plus v sub 3, right? I just solved for v sub 1. So v sub 1 can be written as a linear combination of the other vectors. That's what this first statement means. If we can write right here, if we can write one vector as a linear combination of the other vectors, then the vectors are linearly dependent. Or another way, and we go through showing that, right? Look at this neat theorem here. This theorem is pretty cool. It kind of sums up spanning and linearly independence. So if you have a set of vectors and they go to R, so there are R vectors, and here in the space of Rn, this big space, we say that n is its size. Later on we'll talk about dimension and rank and that kind of thing, but for right now it's the size. I may say dimension, and that's fine. That's exactly what it is. So what you want, the ideal situation is that you want S to have n vectors in it. And so then we get a smooth transition where we can determine linearly independence and spanning. But that's not an ideal situation. So if R is greater than n, if the number of vectors I'm given is greater than what the space allows, the superspace, right? The big space Rn allows. If R is greater than n, then the set, this is the set S, is linearly dependent. In other words, if I have more vectors here in S than what the space allows, I overload or I overcrowd the space that I'm dealing with, and thus I cannot get linearly independence. I get linearly dependence. If R is less than n, then I cannot produce all of the vectors. So then S does not span Rn. That's pretty cool. And we actually saw that for number 2. We saw that in some of the other problems when we dealt with spanning. And I didn't have this theorem. I wanted to say it. I wanted to, right? And we could have just been done with all that crap, right? So number 3, if S contains at least 2 vectors that are scalar multiples of each other, then the set S is linearly dependent. Man, I did have some problems that where you look at by inspection and determine, and boy, I'm crazy. And coming off this sickness, this COVID-19 is just kind of fried my brain. But to tell you the truth, my brain was already fried before. I had a professor in graduate school. He used to laugh like that. I think he was from Finland. I love that guy. He was pretty cool. Okay, let's look. Determine whether the set S is linearly independent or linearly dependent. So we're given 2 vectors. Here's the argument. And so let me go through the argument with you. To determine whether or not vectors are linearly independent, based on how many vectors we're given, v1, v2. We must be able to find scalars. Here, based on how many vectors we're given, that's how many scalars I need. So K1 and K2 such that K1 times V1 plus K2 times V2 is equal to 0. You're only concerned about 0 for linearly independence and linearly dependence. Right here implies that K1 is equal to K sub 2 is equal to 0. We need to be able to show that, to determine. Right. So I have K1 times V1, that's negative 1, 1, plus K2 times V sub 2, that's 4, 3, and that's equal to 0, 0. Now the system that gives me is negative 1, 1, 4, 3, 0, 0. Now on my graphing calculator, I did that already, and I reduced that to reduced row echelon form. I don't have to rewrite it, I got it right there, but I'm just being a dingy head. So that tells me what? Well, it tells me this. When I read this, this is 1 times K sub 1 is equal to 0. This is 1 times K sub 2 is equal to 0. Well, if I have that, then that tells me that I have linearly independence, right? Okay. All right. Now, this is interesting because look at this. Here with these two vectors, we want to see if we get linear independence. And when I reduce this in my calculator, I get 1, 0, 0, 0, 1, 0. And you say, well, that doesn't look so right. It looks like I ought to have another column over there. Well, let's write it up and make sure we understand it. And when you get the understanding, a little bit better, I think, to deal with linearly independence, linearly dependence versus spanning, because spanning is a little bit more theoretical. So here, to show S is linearly independent, does there exist? Need to say, can we find? Can we find scalars K1 and K sub 2 such that K1 times V1 and this is V sub 2 plus K sub 2 times V sub 2 is equal to 0 implies that K1 is equal to K sub 2 is equal to 0. Well, it's a question, right? So what we have is K sub 1 times V sub 1, that's 1, 6, 2, plus K sub 2 times V sub 2, 3, 2, negative 1, and that's equal to 0, 0, 0. Now, I reduce that, that's what I got. I'm just being a special case and just rewriting it, right? Now watch this. This implies that 1 times K sub 1 is equal to 0, and 1 times K sub 2 is equal to 0. That is the definition for linearly independence. All right. Well, let's look at this next one. Well, here's the thing. If you have vectors, you write the vectors, uh, make them stand up, and if you want, you can check, a couple of things here. You can check -2, 1, 4, 2, 8, -3, 1, 4, and -4. You can see if that reduces to the identity matrix. And it does on your graphing calculator. Oh, that's not right. Jeez. Too much roast beef. Pot roast. That's what that is. And so you get it. That implies that K1 is 0. K sub 2 is 0. K sub 3 is 0. Such that, okay, V1, V2, V3, such that K1 times V1 plus K2 times V2 plus K3 times V3 is equal to 0. And it does imply, because we just check, oh boy, can't see that. Check that in your graphing calculator. So can we find the scalars? And when we find them, are they all 0? Yes, they are. And I can use the equivalence theorem here, what I just used, because for linearly independent, that's actually embedded here. Because to get the trivial solution, you're getting, for this particular setup, well, yeah, that's fine. X sub 1 is equal to 0, and that's equal to X sub 2 is equal to X sub n. They're all equal to 0. So the linearly independence is actually embedded in this guy right here. You could show that A is invertible. Remember, this guy is dealing with the spanning. And number 3 helps us directly with linearly independence. Here, what I just did was to reduce A to the identity matrix. You could have checked the determinant. So any one of them, or if you're from the country, and one of them works. So that was that guy there, right? So having this implies that we get the trivial solution. And thus, if we get the trivial solution, here that means that these scalars, all of them are 0. That gives us linearly independence. Okay, just one more. So here, I'm going to show that this set is dependent or independent. So let's say this is v sub 1, v sub 2, and v sub 3. This is a polynomial in the of two of second degree. So they all must have the form. The form must be like a standard. So their form is a naught plus a sub 1x plus a sub 2 of x squared is equal to some function. So the vectors must be written in that form. So to show linearly independence, now I'm acting on like we don't know what the answer is, right? We must find scalars. How many do we need? 3, because we have 3 vectors. We must find scalars. There's an R in there somewhere. There's gold in them there hills. Scalars K1, K2, K3 such that K sub 1 times V sub 1 plus K sub 2 times V sub 2 plus K sub 3 times V sub 3 equals to 0. Does that imply that K1 is equal to K sub 2 is equal to K sub 3 is equal to 0? Well, I don't know. So we have K sub 1 times that first vector, the first polynomial, which has coordinates 2, -1, and 0. See, it has to have that form x squared. Well, there is no x squared. That means that a sub 2 is 0. Then the next one is 0 because it doesn't have an a naught, right? So it's 0. Then it has 5, -1. The next one, 6. I guess I'm jumping the gun. Plus K sub 2 times 0, 5, -1 plus K sub 3 times 6, -8, and 1. And that's equal to 0, 0, 0. So now you get the matrix up there. So we put this in the matrix. We get 2, -1, 0, 0, 5, -1, 6, -8, 1. Here's 0, 0, 0. Reduce that on your calculator. In order to get linearly independence, the system must be reduced to the identity. It is not. This is what it's reduced to. I'll just put it here. Oops. So 3, not Frankenstein. This is not the identity matrix on that left side. If you were checking the determinant, you would get 0. So since the system could not be reduced to the identity matrix, S is linearly dependent. Okay. Well, I hope that makes sense. Also over here, another way you could have also checked the determinant. You could do that if it's a square system. That is that you have the number of rows as number of columns, um, and so you could pick either one you want to on the so-called um, monster theorem. And I was looking for it. I can't find it. Oh, I have all this writing on it. Yep. So pretty cool, right? Well, I hope you get it. Let me know if you have some questions. Thank you.